Distance learning curricula in machine learning, clustering and its applications. Good afternoon and welcome to the machine learning course. This course was developed as a result of the Erasmus Plus project Coding. All you need to learn is internet access and a computer. The course contains a total of 10 topics, and in this topic we will say something more about the clustering and its applications. Clustering is a type of unsupervised learning technique in machine learning that involves grouping similar objects or data points together into clusters. The idea is that objects within the same cluster are more similar to each other than they are to objects in other clusters. Imagine you have a bunch of items in a messy room, but you want to organize them into neat piles of similar things. Clustering is like that. It's a type of machine learning technique that groups similar objects or data points together into clusters, without needing to know anything about the item beforehand. This helps to find patterns in the data and make it easier to understand. When it comes to clustering, there's no one-size-fits-all algorithm. Different methods have their own strengths and weaknesses, and it's up to the user to choose the right one for their dataset. One popular clustering algorithm is k-means, which separates data points into k-clusters based on their similarity. The algorithm then adjusts cluster centroids until they are as compact and separate as possible. If you want to visualize relationships between clusters at different levels of detail, hierarchical clustering is a good option. It creates a tree-like structure of clusters that lets you explore different levels of granularity. dbScan is another popular algorithm that groups data points based on their density in the feature space. This makes it a great choice for data sets with complex structures, as clusters can be of different shapes and sizes. K-means is a popular algorithm used in data science and machine learning to group similar data points together. It works by taking a set of data points and grouping them into k-clusters, where k is a number chosen by the user. The algorithm iteratively assigns each data point to the nearest cluster centroid and then updates the centroid based on the new groupings. This process continues until the centroids are no longer moved, indicating that the clusters are stable. Think of the centroids in k-means as the leaders of a dance party. Imagine a group of people dancing in a room, and you want to split them into two groups. You ask two people to come to the center of the room and start dancing. These two people are the initial centroids. Now you ask each person in the room to join the group of the person they are closest to. The distance between each person is like the distance between each point and each centroid in k-means. Once everyone has joined the group, you have your two clusters. But the dance party doesn't end there. You ask the leader of each group, the centroid, to come to the center of their group and start dancing. This represents updating the centroid of each cluster. You repeat this process of dancing and updating until the dance party settles down and everyone is happy with their group. And that's how k-means works. Here's an example of how to apply the k-means algorithm to a small data set of 4 points. Suppose you have the following data set. You want to cluster these points into two groups. Step 1, choose initial centroids. We start by randomly choosing two initial centroids. Let's choose points j and I as the initial centroids. Step 2, assign points to clusters. Next, we assign each point to the nearest centroid. We calculate the distance between each point and each centroid using the Euclidean distance formula. Here are the distances for each point. The point H and I are all closer to centroid 1, while other points are closer to centroid 2. So the first cluster contains points H and I, while the second cluster contains other points. Step 3, update centroids. We update the centroids of each cluster by taking the mean of all the points in the cluster. The new centroid for the first cluster is 2.25, 3.38, and the new centroid for the second cluster is 5.0, 4.0. In step 4, we are repeating the steps 2 and 3. We repeat the process of assigning points to clusters and updating centroids until the clusters no longer change. In this case, the algorithm converges after 3 iterations. The final result are 2 clusters. The cluster 1 is containing points A, C, I, F, and G, and the cluster 2 is containing points B, D, H, I, and J. Hierarchical clustering is a type of clustering algorithm that aims to group similar objects or data points together based on their proximity or similarity. The term hierarchical refers to the fact that the algorithm creates a hierarchical structure of clusters, where the clusters can be nested inside one another at different levels of granularity. The idea behind hierarchical clustering is to start with each data point as a separate cluster, and then iteratively merge the closest clusters together based on some similarity or distance measure. As a result, we end up with a dendrogram, which is a tree-like diagram that illustrates the hierarchy of the clusters. One of the advantages of hierarchical clustering is that it allows us to explore the data and identify clusters at different levels of granularity, from fine-grained to coarse-grained. For example, we can choose to merge clusters at different heights in the dendrogram to obtain different numbers and sizes of clusters. Overall, hierarchical clustering is a flexible and powerful tool for exploring the structure of data and identifying meaningful patterns or clusters. Let's assume we have the following 4 data points. To perform hierarchical clustering, we first need to define a distance metric. Let's use the Euclidean distance between the data points as our distance metric. We start by computing the pairwise distances between the data points and then create a distance matrix as follows. The smallest distance in the matrix is between points A and D, equals 3.61. So we can create new cluster, AD. In step 2, we have to update the distance matrix to include the new cluster, AD. To calculate the distance between a cluster and a single point, we need to find the distances between each point in the cluster and the single point, and then take the average of those distances. In this case, the cluster is AD and the single point is B. The distance between A and B is 5, and the distance between D and B is 4.24. Taking the average of those distances gives us 4.62. Therefore, the distance between the cluster AD and point C using the same average linkage method is 6.74. Here is the dendrogram for the hierarchical clustering of the 4 points using the single linkage method. Starting with data points at the bottom, the dendrogram shows the merging of points A and D to form cluster AD, followed by the merging of AD with point B to form the cluster ADB. Finally, the cluster ADB is merged with point C to form the final cluster that contains all 4 points. The vertical height of each merging point represents the distance between the clusters being merged, which is the distance between the 2 closest points in this case, since we are using the single linkage method. As a conclusion, hierarchical clustering is a way of grouping data points into clusters based on their similarity. The dendrogram shows the merging of clusters, and the horizontal cut determines how many clusters are formed. You can cut at a constant of varying distance, depending on your application. Each level of the dendrogram represents a certain class of data points, but you need to analyze individual samples to offer the common feature. DBSCAN is a clustering algorithm used in machine learning that can group together data points that are closely located to each other. The acronym stands for Density-Based Spatial Clustering of Applications with Noise. It works by finding dense areas of points in a dataset and grouping them together into clusters. In DBSCAN, 2 important parameters are epsilon and minimum points. Epsilon is a distance parameter that specifies the maximum distance between 2 points for them to be considered part of the same cluster. Points within epsilon distance of each other are said to be directly reachable. Minimum points is a threshold parameter that specifies the minimum number of points required for a group of points to be considered a cluster. Points that are not part of the cluster are considered noise. There are 3 types of points after the dbScan clustering is complete. Core. This is a point that has at least minimum points within distance epsilon from itself. Border. This is a point that has at least one core point at a distance epsilon. Noise. This is a point that is neither a core nor a border. It has less than minimum points within distance epsilon from itself. Let's say you have a data set of customer locations for a retail store, and you want to group together customers who are likely to shop together. You could use dbScan to find clusters of customers who are close to each other in physical space. Let's try to simplify dbScan with an example using height and weight data and some calculations. Let's say we have a data set of 10 individuals with their height and weight measurements as follows. To apply dbScan to this data set, we first need to set the values for epsilon and minimum points. Let's assume epsilon equals 10 and minimum points equals 2 for this example. Step 1, choose an arbitrary data point, individual 1. Step 2, find all data points within epsilon distance of that point, those within 10 centimeters in height and 10 kilograms in weight. Individual 1 has 2 points within epsilon distance, individual 2 and individual 3. Step 3, if the number of points within epsilon distance is less than minimum points, mark the data point as noise and move to the next point. Since both individual 1 and individual 2 have at least one other point within epsilon distance, neither is marked as noise. Step 4, repeat steps 2 and 3 for all unvisited points until all points have been visited. The final clustering result is cluster 1, individuals 1, 2, and 3. Cluster 2, individuals 4, 5, and 6. Cluster 3, individuals 7, 8, and 9. Individual 10 is noise. In conclusion, clustering is a powerful technique that has many applications across a wide range of fields. Whether you're a researcher in biology, a marketeer trying to identify customer segments, or an engineer trying to optimize a manufacturing process, clustering can help you uncover patterns in your data that might not be immediately apparent. To complete this unit, study and review the following online resources. Thank you for attention.